Hey everyone. Today what we're going to work through is a little bit of a vocabulary and theory lesson. I'm going to argue that there's not a whole lot of doing today. That really what today is it's a day for us to kind of knock out some new vocabulary, deal with some new terminology, and then address a few problems that'll pertain to it. Really what we're doing though is we're laying the groundwork for the way we're going to talk about almost all of the math that you're going to encounter in the rest of your high school. That really what we're starting to lay the groundwork for is the way we communicate about algebra. So you'll see on the screen in front of you that we have a bunch of terminology. If you're following along with the lesson and we're filling in some blanks, please make sure that we don't just blindly copy down the color, that we're taking in some of the key pieces of terminology that you see. So I want to go through just really quickly and highlight some of them. What we're talking about for algebra is it's simply a language. It's a language that we use to describe ideas. Seriously, it's no different than English, French, anything else. So you start to work your way through then. When we take this language called algebra, we need words, we need symbols, we need things to represent ideas. What we end up using then, variables and numbers. It's important for us to know that all variables represent is an unknown value, something that we are not sure of at the very beginning. The basic units for them, these are kind of like us dealing with letters, spaces, punctuation, all of that sort of stuff in our language. It's the same with algebra. They're all made up of terms. And if you want to think of terms like words, okay, they're like words to us, then the way we can make up our words, our terms, is with a variable, a number, or both. And so what I want to make sure we're good with is that we can jump into some of the specifics of dealing with these algebraic terms. So let's just start off with, I just gave you a sentence. 3x squared minus 5. That represents an idea algebraically. It's expressed in the language of math. Right now, it doesn't really even matter if we understand what that idea is. We can't understand what that idea says until we can break down some of its components. So we have some terminology that we need to get down. Within 3x squared minus 5, we have a bunch of stuff in there. Let's start off with the 3. That 3 is attached to my variable. It's attached to that x. It's attached by multiply. And so what do we call a number that's attached to a variable by multiply? A coefficient. You need to know that term. Okay, so the coefficient on my variable is 3. Okay, well then we get to the x, and the x is probably one of the ones that we would have been pretty solid with. That's the variable of the expression. We talked about that before. Everybody should be really solid with what that 2 is. That's our good old exponent. And now we take a look at the 5 on the end. And I would have a lot of people that would just kind of go like, well, my 5's like my number. And like, they're not really wrong about that. The only issue becomes, but 3 is also a number. So how do we tell the difference between 3 that's attached to a variable and the 5 that is not? The 5 has a different name to it, and it's entirely based on the fact that it is not attached to a variable. The 5 is called the constant, and the reason for it, because it is constant. So what I mean by that is the value of 5 can never change. It is what it is. How much is 5 worth? It's worth 5. Notice that my first term, my 3x squared, the value of that term could change depending on what value we allow x to be. But the value of 5 is never changing. It is constant. So all I want to do now is just get down some examples of what we're talking about with different terms. If we know terms can be made up of a number, a variable, or both, then let's just get down a quick list. So as an example, like maybe I just have the number. We had 5 in the previous. 5 is a term. It's just a number. But maybe I have just a variable. And maybe we go with like a default variable like x. 5 and x are two different terms. But maybe I also have like a combination of them. And so you see a combination up in 3x squared. Maybe I just want to get a little variety. So how about we go like 7y? 7y would be a term. There is a word that's made up of both a number and a variable. Now, things can start to get really complicated. Like maybe my term has a fraction in it. So maybe like 3/4 a. Maybe my term has an exponent in it, like what we see up above. So I have a coefficient, I don't know, 6. I have a variable, maybe I'll c. And I have an exponent, I don't know, let's go ugly, 13. Well, 6c to the exponent 13 is also a term. And then maybe we get into something really ugly, I don't know, like negative 17. 17 is a pretty ugly number. It can be negative, so now we get all of our integers involved. Maybe I have an exponent like x, or sorry, a variable like x with an exponent 2, so an x squared, and I get like a y also. Maybe my term has multiple variables. So I get something ugly like negative 17x squared y cubed. All of those represent different terms. And if we start to take those different terms and we start to put them together, then we start to create a language. So you're going to hear me talk an awful lot as we go about number of terms, about recognizing terms. What's the coefficient of a term? What's a constant within an expression? And so on. That we want to make sure that we're really solid with that terminology. So what you see now is a little bit of a table. On the left side of that table, we have different types of polynomials. And we'll talk about that as we go. We then have our next column that talks about the number of terms within that expression. And then in our last column, we're going to talk about the names of those expressions. Because these expressions that we might have might be special to some extent. So let's take a look at the top row. Now, the question asks us how many terms do we have? And I hope that our eyes will automatically go to that addition sign there. Because we want to make one key note at the bottom, right underneath that table. That when we're trying to decide how many terms an expression has, we need to be able to recognize add and subtract symbols. Because add and subtract is what separates terms. That when I look in that top row and I see that addition sign there, then what I have is one term, 3x squared, added to another term, 2x. And so I think that helps us then to be able to recognize that we have two terms in that top expression. Now, we have a name for an expression that contains two terms. If polynomial is the generic term that we have. Any algebraic expression, and it's not really going to be any, but for right now, any algebraic expression, we might lump into this polynomial category. Then a two-term polynomial expression has a special type of name. And I don't think it should surprise many of us, that it would be called a binomial. Now, when I say it shouldn't surprise us, I don't mean that, oh yeah, I would have had everybody who would have just, yeah, automatically, I know, it's a binomial. No, what I mean by that is, if it's a polynomial, then we shouldn't be surprised that it ends with nomial. Like, that's what polynomial ends with. Poly means many. Can mean. So the fact that a two-term expression starts with bi, like bicycle. Bicycles have two wheels, bicycle. Then I don't think it should surprise us that much. Now, let's jump into that next row then. And I think we should start getting a little more comfortable as we go. Okay, on the second row, I see I have negative 2m. Okay, do I see any add or subtract symbols? No. So how many terms do I have? I only have one. Okay, what type of polynomial is that then? Well, my guess is a lot of us could figure out that it ends with a nomial. And then I might ask you, okay, so what do you think is going to go at the beginning of that word? What's the prefix? What do we end up getting? What would represent 1? Like, we had bi that represented 2. Like, could you come up with 1? And I'll fully admit that over time, I've come to get quite used to seeing or hearing students go like, how about like uni? You know, like you said 2 wheels are on a bicycle. So like a 1-wheel bicycle is like a unicycle. So how about we go uninomial? And I need to say, no, it's not that. But that is very good reasoning. What that is actually called a monomial. For anybody who happens to have like maybe an old stereo at home, or if you wanted to talk to a parent or even maybe a grandparent nowadays, a mono stereo used to be a pretty common thing. And even maybe saying stereo is misplaced in that statement. Talk to a parent, talk to a grandparent about what mono might have meant on a stereo system that you had in your home. They had in their home. They can fill in what mono means, and you can maybe see why that means a 1. Okay, let's take a look at that third column, the third row. Now what you do is you take a look and you say, okay, can I see any add or subtract symbols? Okay, so you scan your way across, and you notice that you have a subtraction here and an addition here. Add and subtract, separate terms. So how many terms do we have? Yikes. We have 3. And here is where I'm going to say I think everybody should be able to fill in what type of polynomial that one is. Everybody should get this one. Even to the point where I'm going to kind of go, I think I should be good to just write that in right now. Yeah, a 3-term expression is called a trinomial. Okay, we're going to fill in that last row together. You have a quick scan and you go, there's a subtraction, there's an addition, there's a subtraction. Those separate terms. So what I have then is 1, 2, 3. I have 4 terms. And I totally get that I would have a bunch of people that would go, hey, that's going to be a quadnomial. And actually it's not. That once we get above trinomial, we actually stop grouping polynomials by the number of terms they have. And we just use the term polynomial to represent all terms greater than 3 terms. We don't specify and break it down. So you take a look at that chart now and you'll notice that we have 4 different types of polynomials that were listed on the left column. And now we can break down our names to them. It's very important that you know the names to those. I would have no problem putting you in a problem-solving situation where maybe I would say, a binomial has blah, 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 blah. And if you were to put up your hand and go, hey, Gray, what does binomial mean? I'm not going to answer that question. So we need to make sure that we know the names of those terms. That's really going to help us out as we move forward. Okay, let's kind of change gears a little bit now. What you see on your screen is a way for us to start to classify polynomials. And what that is it's called by degree. So you see that degree at the front. We have just learned how we can classify polynomials based on the number of terms they have. What we're going to learn now is a different way for us to classify polynomials by something called a degree. So when you see like degree of a polynomial, it's just a way to group them. That's all. It allows us to talk a little bit faster about certain ideas. Okay. Now what you see on the next 2 lines is how we figure out the degree of a polynomial. And it all starts with the degree of a term. So how do you find the degree of a term? You see in green, we add the exponents on the variables. You now take a look at the next question and it says, how do you find the degree of a polynomial? And you almost might say but wait a sec, didn't we just talk about that? And that's why I want you to underline the word term and underline the word polynomial just as I have. If you're writing this down as a blank note, circle them, highlight them, do something to draw your attention to term versus polynomial. We can see in the green writing that to find the degree of a term, we add the exponents on the variables. But in the blue, for us to find the degree of a polynomial of the whole expression, we have to take the degree of the highest term. Okay, I know that this can feel a little confusing because it's all abstract right now. We haven't seen an example of it. But we're going to come back to those definitions. So make sure that we're good. The degree of a term, I add the exponents on the variables. The degree of a polynomial, we use the degree on the highest term. Okay, let's see it in practice. So I've just put those 2 rules again, and that's all they are, is it's just an agreed upon rule, a definition. Right up at the top of the screen so we can see it directly above the chart. And now what we're going to do is we're going to walk through that chart together. So let's take a look at row A. Find the degree of each. That's the goal. So we want to get from this first expression all the way over there to be able to define it by degree. So what we're going to do is we're going to work on it in its bits. So the first thing we do is we have to address the term with the highest degree. Okay, so now I need to figure out how many terms are there. So I go straight to, there's my addition symbol. That separates my terms, and so I know I have one term and I have another term. Okay. The next column says find the term with the highest degree. So I'm going to go back up to my definition of how do I find the degree of a term. And it says add the exponents on the variables. So if I take a look, well, I don't see an exponent on my first term, on my x. But I know that if I don't see an exponent, then I have an exponent of 1. Well, I go to my next term, 3. Well, I already have a problem with that. Because to find the degree of a term, if I look up in green again, I need to add the exponents on the variables. And my number 3, my last term, it doesn't have any variables. It's constant. That means that I can't add anything up. That means I have a value of like 0. Now, to maybe help you out a little bit, I actually do have an exponent of 0 there. And we should remember that really I could add in an x to the 0. Because we know that x to the exponent 0 is equal to 1. And so 3 times 1 is 3. Okay, there was a lot of theory in there, all just to get us to the point where we can now define what the term with the highest degree is. It's got to be my first term. It's got to be the x because that's the only one that has a variable. And so what is the degree, the term, with the highest degree? It is x. What is the degree of that term? So if we're going to fill in the next column, I need the degree of that term. Well, my degree is if I add the exponents on the variables, that means that that is degree 1. And if that's the degree on the highest term, then that is the degree of the whole polynomial. Okay, I think we should be at least a little bit better at being able to go through and figure out the difference between the degree of a term and the degree of a polynomial. It does not mean that we are great at it. No. But it means we should be a little bit better. I think once we go through the next example, I think we're going to be able to tackle some of these on our own. Let's take a look at row B. Okay, the first thing I need to do is I need to figure out how many terms I have. So there's my subtraction sign. I know I have 2 terms. I have a binomial sitting there. Okay, now I need to come up with the degree of each individual term. Well, the degree of each term is me adding up the exponents on the variables. So what comes to mind then is I have, an x squared, and I don't see an exponent. I know that that means 1. So that means that I have my first term that is degree 2 and my second term that is degree 1. So which term then has the highest degree? Well, it would be the term 5x squared. What is the degree of that term? It is degree 2. And therefore, what is the degree of the whole polynomial? It is degree 2. So if we were to jump after those first 2 problems now, if I gave you the expression x plus 3 and asked you what degree was that polynomial, you would tell me the whole polynomial is degree 1. If I was to give you 5x squared minus 7x, an uglier looking expression, and I asked you what was the degree of that polynomial, it is degree 2. And we can see why that is the case. Okay, what I want you to do is to work your way through C and D. If we're still a little unsure, then unpause the video and we'll make sure that we match up on C, and then repause it if we're feeling more confident about D. But right now, I'd love you to try for both of those last 2 rows. Okay, pause it now. Okay, we're back. So we take a look at that expression, and you notice you have an addition and subtraction. That's breaking up, so we have 3 terms. You notice your exponents on each of those terms, and we should see that that cubed is the highest exponent that we have. That makes that the highest degree. That degree is degree 3, and therefore the degree of the polynomial is 3. Okay, now we're working our way through D. As we take a look at D, nothing changes. How many terms do we have? We only have one addition sign in there, so we have 2 terms. I take a look at that, and yes, my terms got uglier. Now they contain 2 different types of variables. What is the definition for how we find a degree? We add the exponents on the variables. Okay, so I take a look at my first term, and I need to add up those exponents. Hey, that's a 6. That makes the degree of my first term 6. We may, if we are a little careless, take a look at my second term and say, hey, I've got a degree or an exponent 6 there. Both of those terms are the same degree. And we would have made a big mistake. Remember, if we don't see an exponent, we know that there's one there. And so when I add up the exponents on my second term, I see I actually have a degree 7 term. That then makes x to the 6th y the term with the highest degree. Because that degree is 7, which makes our whole polynomial's degree 7. So, as we're working our way through, I am hoping that that just kind of gives us something to give another way to group polynomials. I am not saying whatsoever that that makes sense to us at all. Instead, what I'm hoping is just that we've kind of learned some new terminology. We now know how to group polynomials based on the number of terms. And we also know now how to group polynomials based on degree. It's some definitions that we just got to get used to. Okay, what I want to do is mention one other piece of terminology. What you see on the screen now describes 2 different ways that we can represent our idea. If you look at the top of the screen, it asks me to write each one of those polynomials in descending order of x. Descending order. You then look at the next question in about the middle of the screen, and that one tells us to write it in ascending order of x. So what that means then is there must be a difference between descending order and ascending order. And I am hoping that even just hearing the word descending makes us think about going down. You know, you descend the stairs. Descending order. So when it says descending order of x, what that's making reference to is my degree of x, my degree of each term. So when we take a look at the question in A, descending order says, take that big bunch of terms and rearrange it so that my exponents are in descending order. Okay, so I take a look at all 4 of those terms and I say, okay, well, which one has the highest exponent? It's that 5x cubed term. So 5x cubed must go first. What has the next lowest exponent or next lowest degree? Well, that's going to be my first term, my 3x squared. Notice the sign in between those terms. It has to be a positive because look at the sign out in front. That is a positive 3 on that term. I'm not changing any signs. I'm simply rearranging. Okay, what's my next degree? Well, my next one would be that minus 2x, because it has an x. I know that if I don't see the exponent, it's an exponent 1. And what has to come at the end is my constant, because I know if I was to include a variable, it would have to have an exponent of 0 on it. There are 0 x's in that constant. There we go. So if you have that read, then you have rearranged that polynomial and you have written it in descending order. I need you to know that descending order has a special name to it. It's called standard form. And the fact that it's called standard form, that it's the standard, should tell you that you're going to write most of your polynomials in standard form. We will discuss the times at which you break that rule. But right now, if your default becomes standard form, then you are good. Okay, what I'd like you to do is now to try question B. I want you to write that polynomial. There's 3 terms in it, so it's a trinomial. I'd like you to write that trinomial in descending order of x. Okay, pause it now. Okay, we're back. So now the only difference was my terms have multiple variables. But all I'm focusing in on, the problem says, the descending order of x. So that means I need the highest power of x first. So we need to have a negative 7 x to the 5th y. And then my next highest power of x, well, we jump all the way down to just x to the exponent 1. And then at the end, my good old constant. There we go. Okay, I think with no other instruction, no other discussion, everybody should be good to be able to take that last polynomial and write it in ascending order of x. Okay, pause it now. Okay, we're back. So we're looking at ascending, and I'm hoping that we can look at that and say, hey, that's the opposite of descending. Ascending is us going up. It's rising. So if I'm going ascending order of x, then that means I need to have the smallest number of x's first, and then I grow to the most at the end. So when I scan down, I notice I have 1 term, 2 terms, 3 terms. I have 4 terms. Then I'm looking for the smallest exponent on x, and I am hoping that we put our constant first. If we're going to have ascending orders of x, then I'm going to start with what I have no x's with. That is my constant, no x's. Now I grow and I notice that I have 1x in the term 9xy to the 4th. I notice that I have 2 x's in x squared y to the 7th. And you're paying close attention to how I'm reading these terms, how I'm talking about these terms. And then we have the most number of x's in our last term of negative 6 x cubed y squared. And there we go. If we got down to that, then I think we are good. Now that we're done everything, I hope you can see why I said at the beginning that really what today is it's just a bunch of terminology. We learned some conversation about variables and numbers leading to terms. We addressed coefficients versus constants. We learned how to talk about polynomials by grouping them by number, but also grouping them by degree. And now in the end, we're able to rewrite our expressions in different possible forms. Okay, today was hugely important, though, for laying the groundwork for how we talk about our ideas going forward. So your job is to make sure that you're comfortable with this new vocabulary and to make sure that we use it when we talk about these expressions. Okay, jump in, get some practice. Best of luck.